Michael Huth from Imperial College, and I know you've done this a long time ago, but I can't help mentioning, Michael, that you are a co-author of a book that is very widely used on logic in computer science, and so here you're only known as Michael Huth because we all thought you were American. So, but Michael actually, I'm saying Michael now. So Michael actually has a very interesting career also now in XAIN. I'm sure you're going to say something about it, addressing, I think, something that has to do with the fact that there's a real world and there's a digital world, so how can we make them all to come together? Welcome.
Thanks very much, Fritz. Thanks for being here. I want to thank for the invitation as well. So the book that Fritz has mentioned was actually written with Mark Ryan from University of Birmingham as well. And yeah, so I wanted to tell you about some work we've done in this startup XAIN. So it's a company headquartered in Berlin. It's about 25 or so people, 60% engineers, strong capabilities in AI, in particular collaborative AI, but also in cybersecurity. And today I want to focus on the cybersecurity work. I'm also a professor at Imperial College London, so just a few facts about that. That's one of the leading universities, actually came out of the Great Exhibition a good 100 years ago, which in today's language you might call an incubator. And so in a way, tech transfer and knowledge transfer is part of the Imperial DNA. Okay, so I wanted to put up this slide just to get us going. So we've heard a lot about blockchains and programming languages and all these sorts of things. These are very important in this digitization of the world we're going to live in. But also we're kind of starting from the other end of this. Yes? So we were actually engaged in a design context with Porsche. I'll tell you a bit more about this later. And so we kind of got sucked into automotive and their problems. How can we make sense of this digitization and the sharing economies and all these new dynamics? And so I put this up here just to illustrate the complexity of a modern vehicle. Yes? So we're going to look at a car, and this these days has about 100, 110 computers on it, electronic control units, a whole network, internal vehicle network, with intrusion detection between nodes and all sorts of stuff going on. But then we have gateways into this network that mediate to the outside world, and so we have some offerings for that. If you think about what this means in the future, there will be so many data streams coming out of vehicles that are basically untapped at the moment. For example, monitoring the lubricant usage in your vehicle, which the producers of these lubricants will be very, very interested in getting. So there's a payment angle here too. If I, as an owner, could actually sell this data to the manufacturers, there's a payment stream that I don't necessarily want to put into a cloud, but maybe just do quite directly through the vehicle. Yeah? So you're seeing basically vehicle to X, where you connect into persons. The person who walks up to the car gets automatically scanned and identified, and then the car usage is customized to that individual, for example. You see vehicle to network, which is certainly of great importance in autonomous driving or semi-assisted driving, but also vehicle to infrastructure. So we hear a lot about electrical vehicles now. They need charging stations. This is a fairly complex sort of infrastructure, quite costly. So there is a benefit of synergies between the networking, the infrastructure setup, and economic incentivization in all of this. Yeah? So just to say, there's a very complex kind of landscape here where there's a lot of business cases. For example, let me just highlight one here, a numerical passport. So Renault, for example, went public saying they're very interested in this kind of concept, as are most other automotives. The idea basically is, once you've manufactured a car, you want to have access to some key data of that particular car over its lifespan, so that you can basically learn more about your own model type, its weaknesses, how to improve it, but also you can actually attest that certain things in this vehicle have or have not happened. Insurance, crash incidents, and so on. But also saying this is actually the mileage of this car. No screwdriver manipulation of the reading of that. Yeah? So there's just one potential business case here. But the problem is, in a way, how do you actually realize this all with technology in a way that's trustworthy? And so XAIN was engaging in a design contest with Porsche, which they won. It was like 140 or so participants. And Porsche was basically interested in realizing a couple of epics. which in a nutshell was basically saying, we will give you a Porsche Panamera for 6 weeks or so, and you can open up the hood and basically connect to the vehicle system through a Raspberry Pi and see what you can do with that with blockchain to enable services and novel applications. And so we see here car sharing in terms of, a delivery person might walk up in this epic here to a trunk and basically get the right to open that trunk just for a certain period of time to put in a parcel or the laundry or whatever it might be. And then here I already mentioned the lubricant monitoring as an interesting use case, or simply the delegation of usage of your car to maybe a family member or a friend, these kinds of things. So that's something that we realized. You can go on YouTube and just search for XAIN Porsche to see a 6-7 minute video on that. So we don't really have time for that. I wanted to show you really today on the research side the sort of thing that came out of doing this proof of concept. So we kind of hacked into the Porsche vehicle, connected that up to the Raspberry Pi, connected that to Ethereum Go client, and did these things, right? But there were a couple of lessons we learned also when it came to the kind of security architectures we would really need here, keeping in mind that at the end of the day, this cannot run on a Raspberry Pi. It will have to run on commercially used microcontrollers, which are much more restricted compute environments. So this is where we came into this technology stack for trusted access delegation, which we are developing. And it's called FROST, basically for flexible, resilient, open, service-enabling, and trusted. So just to say, it's flexible because it's actually not vetted into a very particular sort of syntax. So this is attribute-based, meaning, particular needs and use cases can basically define their own attributes to realize what they want to do. Resilient simply because we are using cybersecurity protocols and perhaps blockchain hardening in the back. Open because we really think of this as an open development where a lot of the stuff will be open source. Service enabling, the epics I showed you on the last slide attest to that, and basically trusted, trustworthy through a combination of all these kinds of measures and technology. So maybe, I'm not sure how I can actually click on this link. Is that something that you guys can do? Oh, interesting. Someone must have that screen, so sorry. I guess yes, right? Yeah. Okay. Yeah, we clearly did rehearse that. If it does get too complicated, we'll just skip it. Yeah, okay. So maybe I'll just talk you through this in the abstract. So what we did here, and you're invited to look at that later, is we basically took a microcontroller from Infineon Technologies as is actually used in a vehicle, and we connected this up to smartphones, so we could basically demonstrate how someone who has an app for a car can basically edit in that app delegation rights to other individuals, and then this update of the policy would be propagated on the network, and once this network update had reached the blockchain, this would be certified, and after the certification, maybe I'll just be quiet then. Do we have sound? Okay, so great. So I'll just talk you through that then. So here you see the two smartphone apps. So this is the owner actually controlling the car. This is the one who doesn't own it, so he can't really do anything. Rights are indicated by little LED lights on this microcontroller here. This is a Porsche that you can buy online, but it's actually heavily fitted with other hardware we had to put in to actually control the doors and the lights and so on. And so here you basically see the owner has certain rights, like to open the trunk or to open the doors, as you can see here. So this is actually now releasable, and you can close it again. And then, what we want to do next is we would like to grant Leif these kinds of abilities. And so we can go to a delegation editor. This is just sort of a prototype. This wouldn't be the actual user experience, obviously. So you can basically select an individual, select the action type, like open trunk, time box this within a certain window. Since we're based on attributes, we could also use geofencing as another sort of constraint. And then this basically gets uploaded into the network. And then eventually this will be mined. So this is our Go client that we were writing on a private Ethereum network. And then the phone basically gets the update from the blockchain, loads the policy onto its own phone, and then basically the Infineon controller also has the policy here and has certified it from the blockchain and starts executing this. So in a way, this is an access control architecture, as you might know from enterprise settings, but the difference here is that this is actually sitting at a microcontroller at the IoT endpoints of the moving device in this case. Yeah. Okay, thanks very much. So, just to recoup that then, so the workflow is that someone who's in control of a certain thing like a car can delegate access, and here we have just written a bespoke version of what we call proof of kernel work, which is actually what Silvio this morning talked about. This committee selection mechanism is the same mechanism we're using here, although we are using proof of work for this, so this scales in the same sense. And then, once consensus has been established, the new or updated policy can actually enter the microcontroller, and in its own stack it will now have a certified update, and therefore when the next request comes it can check, is this actually okay according to the updated policy, and then it can talk to the vehicle system, in this case the network, to enact the command. So this gives us blockchain here, in a way gives us a much harder sort of resiliency of the change management and the lifecycle management of these access control and usage control policies. Okay, so the control architecture we're using here, the experts might recognize this. This looks a lot like the XACML type architecture. I just maybe want to highlight what might be sitting on the device. So there is a policy administration point where the policies would be stored. They come from the network, maybe through blockchains, as we saw in the demo. Then when requests come in, they will be evaluated according to the respective policy. A decision will be computed, perhaps some obligations too, which might be payments in lots of applications. And then the policy enforcement point takes all this information and tries to enact this in the real world. Yeah? So in this case, actually, it would be a communication to the vehicle network system, which might even override some of the things that we would recommend here, for example, for functional safety. Yeah? So this is just an abstraction layer here for basically enacting something that the user really wants, but there might be some other things that stop them from doing that. This is probably not an issue in most real applications. The other crucial thing is, since it's attribute-based, we have a lot of attributes whose values we need to determine in order to evaluate the actual decision. And so this might come from sensors in a vehicle in this case, or it might also come from external information. Yeah? So we need a trusted way of getting these attribute informations, and again blockchain might have some interesting things to offer here to get more trustworthiness. So in a way, this is the architecture. A use case of the language is a rule that says grant if the object is a specific vehicle, the subject is the daughter of the owner of the vehicle, the action is to drive the vehicle, and if the daughter happens to be insured, and this is actually within a certain time window. Yeah, just a little example to illustrate the kind of rich things you can program here, although the actual programming structure is very, very, very simple. The complexity really resides in the openness of the attributes and their meaning. Yeah, so that's the trade-off that we're doing. So you could even do things like diesel particle filter regeneration, which of course with the diesel scandal and so on might be quite an urgent kind of thing to support. In terms of verification, let me just highlight this thing here. There's a nice bug here, so this is saying local time should be after 9 in the morning and after 8 in the evening, which doesn't seem quite right. Yeah, so you probably want to switch this inequality sign here. So I think it just illustrates, how these things can just kind of happen, and so verification should certainly flag up these kinds of issues. Okay, now let's talk about semantics here. Why do I talk about semantics? Because I need to talk about the composition of usage control policies. Yeah. So take, for example, the car manufacturer, they want to have the numerical passport. That's one policy that needs to live on this vehicle. The car dealer wants to have a policy on this thing. Yeah? Some leaseholder and their family members or so might want to be able to put policies there. Now, they need to interact in some sort of sense. Yeah? So I have to have a way of achieving this. Obviously, I want to be able to deny a request or to grant a request. That's the bread and butter of access control. But because of this open-ended nature of composing different policies that I don't maybe know ahead of time, I need to also at least have two more values here. One of them is conflict, which basically means for a particular request, I have conflicting evidence according to my policies. Some basically say I should grant, the other ones say I should deny. So I want to have a way of raising this into the language itself that this has happened. Similarly, in open systems, I might get a request where parts of this I can't even interpret. I've never seen this before. Yeah? So it's an open data model in a way. So I have to be able to say that I don't understand this, that this is undefined. And that's a minimal sort of semantic space, which is actually going back to AI research, I think is late as the late 50s or so. So these structures are called Belknap lattices. They have two orders. This order going up is the information ordering. You could almost imagine, here I don't know anything. When I grant or deny, I know quite a lot. When I have a conflict, I basically have too much. Yeah, I have information overload. It's conflicting. Whereas the truth ordering going this direction is basically increasing the goodness of the request in the sense that things are really good when I grant, things are really bad when I deny. Yeah, so that's the intuition of this ordering. This ordering is important for cybersecurity because I may not have all the attribute information available at real time. So in a way, what I want to make sure is that an adversary, an attacker, cannot somehow move up in this order of making a decision by withholding attribute information. Yeah? So it's a very nice, clean, logical way of ensuring this. Okay, the language is really not a language. It's just a coding idiom. So you might implement this, embed this in Haskell. You might embed this in all sorts of other languages. We've embedded it in C because it had to run on a microcontroller. You could do this in Rust, which also runs on microcontrollers. So let's just have a quick look at this. This is an encoding of the information join. If I had two policies, P and Q, say car dealer and manufacturer, what would the join be? It's basically the lattice theoretic join of the information. Yeah? So we write this basically by saying, if the policy on a request evaluates to undefined, the result should be whatever the other policy says. Yeah? Dually, so that's a symmetric definition. If one of them reports a conflict, the overall should also be conflict. However, if each of the individual policies give me explicit conflicting information, the result should be a conflict. In all the other cases, they both will actually compute the same result. You can sort of go through that in a quiet minute, and so you can just return P, say. So this really captures that deny, grant, the join is conflict, and so on and so forth. Yeah? So notice the programming pattern. We have basically case statements with continuation policies, but where the cases are simple conjuncts, but the conjuncts really just appeal to the outcome, meaning the decision of a sub-policy. Yes, so you're kind of forcing the programmers into thinking about how do I combine these policies? What's going to happen in which scenarios? So this makes to us a lot of sense. So this has also one side effect that we can basically take this 4-valued policy and compile it into two-valued policies without losing any information. Yeah, and that's important because microcontrollers like these two-valued kind of things. Yeah, so in a simplified way. So how do we do this? There's various ways of doing this. One way is to say, I'm going to look at two sets. The first one is saying grant or conflict. The second one is saying deny or conflict. Yeah? If I know the membership status of an element in here in those two sets, I know which element I'm talking about. For example, the element deny is the unique element in this lattice that is in this set and is not in that set. Yeah? And so you can do similar insights for the other elements. So this basically gives us a way of representing policies as conventional two-valued circuits. I just need two of them, yeah, for each policy. So here, just for the programming language aficionados, you can see sort of a seed of a core language where we have the compilation rules that basically compile a policy into well, grant or conflict condition or a deny or conflict, which I didn't put up here. But the upshot of this is this equation here. If you give me a 4-valued policy, I can compile it into 2 logical circuits, grant or conflict and deny or conflict, such that the policy is the same as the information join of these 2 simple rules. Yeah? So I'm basically saying, here are all the scenarios where the policy grants, here are all the scenarios where the policy denies, and I just take the join of these 2. Yeah? So this gives me the full picture of the policy. What's also nice about this, I may think of this as a compilation into logical circuits that are going to run on a board, as we saw in the video, but I can equally use optimizations like binary decision diagrams when I interpret these logical operators just over those optimization data structures, or I can actually interpret this as generating verification code, just assert say for an SMT solver if I want to do some analysis. So here maybe just 2 examples of policy verification. This one is kind of about integrity checking. Here's a circuit C, and I'm already knowing or believing that the policy P never returns undefined and never returns conflict, so I can just take one of the circuits, one of the 2, and I want to make sure that this circuit really has the behavior of this P, which might be living in the cloud and has a hash in a blockchain. Yeah? So how do I do that? Well, I generate the circuits for the policy, as sort of hinted at in the previous slide. I then check whether the negation of both circuits conjoined is unsatisfiable, because that's actually saying if it is, then this policy could never return undefined. Yeah? So this comes from the nature of what this compilation actually achieves. Dually, if I take the same circuits and I just conjoin them without negation, if that's unsatisfiable, I know the policy has no conflict. Yeah? If all of these tests pass, I can then simply ask, is the logical circuit logically equivalent to this one circuit here? Yeah? This is now all in the same language, so I can check for equivalence. And if they are, I really know that this circuit that I might want to run on this microcontroller is really giving me the same behavior as this policy living up there in the cloud. Yeah? So it's just one example of how we also can reuse this compilation technique for verification. And here's an even easier one pertaining to change management. We often need to update these kinds of usage control policies. So I might want to make sure, is a new policy P prime that was updated from a policy P, is that more permissive? Yeah? And here I have one interpretation of more permissive. Maybe I say the updated policy doesn't grant whenever the old one denied or was replying with undefined. Yeah? How can I assure that? Well, in the compilation, it turns out that I also need an auxiliary compiler that gives me the exact condition for these expressions here to be true. Yeah? So this is basically saying it's the exact logical condition for this policy to evaluate grant, to basically grant, and so on. And now this is basically my analysis, and it basically is almost like the English I've written up here. This says the new policy grants and the old policy either returns undefined or denies. So I want to make sure, can I make this true? And if I can make this true, this is basically a bug for this update consideration that I have. So we see that this compilation that we're actually realizing on the microcontroller has quite a few other uses, particularly in verification. Okay, so I already talked a bit about withholding of attribute information, so we really exploit this truth ordering to make sure that whenever signals are maybe not available or some active attacker actually withholds them, they can't use this to escalate privileges, to move from maybe an undefined to a grant or something like that. So that's quite important. We can also eliminate dead code in the case statements. So this is quite important because the programmer, we talked about programmer intent this morning. So they might have a certain intent when they write things, but maybe if one of the continuation policies can never be reached semantically, there's some sort of issue here. They must have misunderstood something or overlooked something. So there's actually some value in verifying the front-end language as well. Whereas we don't need this, strictly speaking, when we compile, because if something can't be reached, the compilation will just not generate it. So this is a sort of a separate point. Now, we also have a way of realizing another form of delegation. So the video just showed you delegating, being able to use the car to a friend, say. But what about delegating as, say, the owner, the car dealer, to a manufacturer, the permission to load a policy onto the vehicle and to interact with their own policy in a certain way? Clearly, you will need this sort of thing for like a numerical passport. So we have cybersecurity protocols that can do this. Let me just give you a rather simple example where you might have a delegation chain. Yeah? So the owner of the resource, say a game controller, might delegate this ability of putting policies on the game controller to this person, who might further delegate it in some sort of chain. You might cut the depth here, which the owner might control. And the owner also controls the composition operator for the policies that these agents will then select. Yeah? So just to make sure, P0 is the policy that the owner selects. P1 is the policy that the initial delegatee selects, and so on and so forth. Yeah? So your teenage kids might also want to put some policies on the game controller, but you might want to be in control of overall usage time and so on. Yeah? So this just gives you a priority composition operator here, which encapsulates this kind of priority of controls. And the cybersecurity protocols that we have basically allow a microcontroller to receive these entire chains, check their integrity, and then deploy the policies along with the composition operators. So I would like to kind of conclude then maybe on this slide here. So in a way, what we have done is a couple of POCs, as were mentioned in this morning. We've also done a minimal viable product with Infineon Technologies, but we're now also working with an actual car manufacturer on, not quite sure what the right word for this is, but staged POCs where there's a very, very clear intent of moving decentralization technology into production. And so this trusted access control stack and usage control stack that I've shown you would hopefully be a big piece of that. And we really want to push this out as open source, meaning the core of this technology should become open source. And one of the inspirations we're drawing from here is really from Volvo. So I didn't want to show you the image of the actual engineer who invented it because I wasn't sure about the rights of the image source. So this is just from Wikipedia here. What you see here is a 3-point seatbelt. Yeah? And so this was invented within Volvo. I think Volvo filed a patent for it. But then they also did some initial tests, and they began to realize what the health benefits would actually be. Yeah? And then they really decided to let this patent go. So just to quote from their managing director, the decision to release the 3-point seatbelt patent was visionary and aligned with Volvo's guiding principles of safety, which is still a core of its brand, I would say. And so really we want to sort of see this, not that we might want to make these big claims, but we see ourselves in a very similar spirit on our cybersecurity work, that we really want to offer this, and we would love to engage with the academic community on the research side of this. This is a very, very demanding space in microcontrollers where you have so limited resources, and you do actually want to have a lot of assurance when this kind of stuff goes through that we saw at the beginning. You can just again get a sense of how much is going to happen here, and how many payment streams are going to be opened up that are mediated through the vehicle. And that's really why I chose this title, that you're really sort of turning a vehicle into an economic platform. So with that, I just want to thank you very much for your attention. I know it's late in the day, and I'd be very happy to follow up, be it commercial or be it research, and here are my contact details. Thank you very much indeed.
We have time for questions.
Thank you very much for a beautiful talk. When you have 4-value logic, is there a possibility for more?
Thanks for the question. So the extendable access control language standard 3.0 actually has something like 7 values or so. Yeah, that's an interesting question. I think we thought about this a bit, but when we also talked to clients and so on, it became quite clear to us that this is probably not the right way forward. My answer to this is maybe, if you need more than 4, you want to add that complexity into the conditions in the rules. Yeah? So if you have, for example, something that says, oh, I have a fault or something, if you think of this as a semantic value, that should actually be a trigger and a condition that somehow informs what the actual decision is in the policy. So we have really a minimal support for open system composition, and these kinds of considerations, I think, are part of the ontology of writing logical expressions, perhaps.
May I just interject? Not a question about, SAT solving and incomplete problems, but about the IoT devices. This is actually highly programmable IoT devices with policy loadable. And most of the IoT device manufacturers nowadays, they want, and I understand them from their perspective, they want you to actually equip your equipment with IoT devices so that they can gather all the data about you in cloud solutions. Now, the question is, how does this IoT model that you're proposing here interoperate with the notion of blockchain as a decentralized system, and there's a little follow-up then. Yes.
Yeah. So in a way, I mean, the Frost technology as such is agnostic, to what sort of data backends you're using. I mean, we've also done sort of POCs with conventional distributed databases, but certainly blockchain or distributed ledger offers really interesting things in terms of finance, like we heard also this morning, to do micropayments, also a bit more cost effectively, in this kind of space. But yeah, I mean, I would say this question of whether something should be on the cloud or happening really on the edge as computing, I'm not sure we have a strong position there, but we do have maybe a value here where we really think that the owners of those resources should somehow be in control of how this actually plays out. Yeah, so this is maybe not so much one of the big sort of cloud providers being in full control, but rather the people who have these resources should have a say in who can interact with those resources in what sort of ways. Yeah? So, which is also partly why we think programming this from the vehicle or from the e-scooter or from the motorbike out and just thinking of this as something I could connect with other things as maybe being able to achieve those kinds of values.
So, I mean, you may have answered this one. So in particular, you can have multiple data collectors and aggregators.
Oh, yeah. So thanks for that. I'm not sure if this rolls over. No, it doesn't. So, in the first slide, we basically might have a blockchain just for distributed identity management, yeah, for the vehicle-to-person walking up, yeah. We might have a blockchain just for doing the payment streams for the lubricant sort of data, yeah. We might have yet another blockchain that, as we do actually have one our own, for managing the life cycle of the policies and their change update, yeah. So I think this is just this kind of picture. I don't think we will see a single backbone, sort of like the internet, Vint Cerf's wonderful stuff. This was a very universal service. I don't think we will see this in this space. There will be lots of things composing and connecting with each other.
Great. So before we leave, I can't help mention at the end your comment about interacting on open research and the Volvo quote. It's interesting to see a Volvo quote like this, and your encouragement as a CTO of a company in the context of, for example, what I just answered to the universities by measuring our impact by actually counting the number of patents we file and how many actually closed interoperations and interactions we have. Yeah. So it seems like Volvo and maybe you are the kind of open dissemination providers of the future. So thank you for that.
Thank you, Fritz. Thanks again. Thank you very much.